All right, welcome to class today. So, an update, there is going to be a change in the exams. There was some lab misscheduling, so I thought I had the lab scheduled for the semester, and they informed me yesterday that it is not. And so, we're going to be moving it to February 3rd, which will be the Monday after it was on the schedule. So, do let me know if you have any issues. Yes?
What time of day just in this class?
So it will be actually in the Ingman and then the room that's right next to the Ingman.
Like same time?
Same time,
Okay.
yep. It will be the same time. It will be designed to do in 50 minutes.
Okay.
So you'll be able to start and end.
Where is that room?
It's upstairs. So if you go down which direction, north from here, down the hallway, there's a door there. If you go up to the second floor there and then out.
Okay.
So.
What's the name of the room again?
Ingman. So it will be the Ingman lab. If you want to go find it beforehand, 210 and then L208. So we'll be in both those rooms for that. You're welcome again to bring your own computer. If you would like to just do it on your own computer, that's fine too. All right, any questions about upcoming exam? Okay, do make sure that if you haven't completed the quiz today, do make sure to take that quiz. So it's voltage and current dividers. So do make sure that you complete that quiz. Sorry, I saw somebody was still taking pictures, sorry. Saw it up and then you.
Post on campus, I'm assuming.
I'll send out an announcement with the updated schedule on there too, yes. But I did want to give an update today about that. Okay, last time we talked about making sure to being able to identify branches and nodes, understanding that there's one current in every branch. So a branch is between two extraordinary nodes. Every branch has a unique current to it, so but only one current, but can have multiple voltages in there. And then a parallel branch will have one voltage across each branch if they're in parallel and have the same voltage. So one voltage across branches or across parallel branches. And then each current, since they're separate branches, will have its own current. So that concept is very important to understand. Every element, another one to make sure you understand, is that every element has voltage and current across it. So if you have a current source and there's no voltage labeled, it still has a voltage across it. So make sure you understand that seems to be the one that most students miss. All right, so last time we had talked about the different currents. We identified all these branches and then defined that there was 7 currents here. So now, on this one, how many different voltages are in this circuit? How many different node voltages, I should say? I'll say hint. Okay, so I'm going to label a ground here. So labeling a ground puts that location at 0 volts. So if I label this one here as 0 volts, this would be one unique voltage. So count that as 1. And then determine how many other nodes have a unique voltage on them. Does that make sense what I'm asking? Okay, so think about this for a minute and then put it there. There we go. me see, there we go. Okay.
So is it those voltages specifically that all voltages?
It seems like the answer is between 7 and 11, so somewhere in there. Kind of interesting. Okay, so let's talk about this one. So these are already highlighted, but now we want to find actual voltages. So last time we labeled these, this would be an ordinary green. Ordinary node here, extraordinary here, ordinary here, ordinary, extraordinary, extraordinary, extraordinary. And then the bottom, even though they're separated by wires, they're still the same node. So I have 0 volts here, I have 0 volts there, I have 0 volts there, I have 0 volts anywhere on this wire that I measure. I'm going to have the same voltage across any part of that wire. So that's why we want to highlight them, is to identify, like, even though physically that looks different, it is the same voltage anywhere on a wire. Does that concept make sense? Okay, seeing some yes, some still no. Okay, I'll keep repeating it. Hopefully that will get there. Okay, so voltages themselves. So what is the voltage here if I labeled this V1? So
6 volts.
correct. So wherever I label that, that means I'm comparing it to ground. So that's why I put a ground in there. So the ground is necessary to be able to understand at a node the difference is always compared to ground. So we don't label it from there to there. We can say it's, plus to minus between that whole thing, which is the same as 6 volts. But if a label is there, it's implied that it's always comparing it to ground. So we want to put in a ground in our circuit so that you can have that reference point. So if I have 6 volts here, then I go across an AC source. So I'm going to have AC and DC at this point. We'll not talk about AC portion yet, but this would be then a different voltage than it would be at V1. So we have V2 here. Here we would have again another voltage, V3. Is this V3 voltage or is this something else?
Something else.
It would be something else, good. So this would be, I could label it 4. And then at this one, is that V3 or something else? Something else again, so we have 5. What about here? Is that V5? Nope, it would be something else, so V6. What about here? That's still going to be V6, that's the same. Hopefully you're seeing this. What about the orange wire? What about here at this point? Same as V6 or something different? Different, so V7. What about here? Good. So this is same as V7. Anywhere on this wire, so here also? V7, so same. What about here? Do we already know this voltage? 0, correct. All right, the only one that's not labeled now as far as a node is this point. Is that the same as anything else, or is that different? Okay, so this would be 8 plus ground, so it'd be 9. Different voltages in this circuit at nodes.
How the yellow on the right is the extraordinary node?
Sorry, which one?
The yellow one on the very right next to the orange one, how is that one?
Sorry, it should be ordinary.
Okay.
I did mislabel that one. Thank you for catching that. That is confusing. That's an ordinary node. Extra, make sure I didn't make any others. Ordinary. Okay, yeah. So there's just the 3 extraordinary, well, 4 with the ground, but we labeled the ground as 1. Yes?
So V1 and V2 are different because of the divider between, or the current, or the battery or whatever that is between
Yep.
them?
So because you have an element, any element's gonna have voltage across it and current, remember?
They're just labeled with the same color, so I was a little bit confused, but yeah.
Yeah. So every element has a voltage and current
Okay.
across it. And that's gonna therefore change for V2. Does that make sense? Okay, other questions? Okay, so this concept is very important to build on for all going throughout the semester. So I'll keep hitting it. So we'll keep doing some of these more and more exercises. So now I've labeled the ground in a different place. As I said, I usually like it on the bottom, but what if it is not on the bottom? So think about this one for a second and try and find the value for V2 here. for those that want some additional practice. So what about if I labeled that as V1? What is the voltage just across that resistor? And I'll also do this one, V3. Okay, so we know that all of this is the same voltage. So anywhere on that wire is going to be minus 32 volts. So that's given to you. And then I'll label them different, each of those nodes has also the labeling of that voltage. That again is meaning that from that point to ground is that value. So from this point, which is part of the yellow wire, to the green wire is 10 volts. You guys see that? Okay. So if that's 10 volts, and I want to find the V1, and I know the bottom is going to be minus 32, it's implied but not drawn that this is from plus to minus here. So if I want to take a loop, and I go from ground in this direction, this would be a plus, minus, and then going through V1, it puts us at a minus. So plus 10, minus V1, minus, oh sorry, I labeled both those are V1. I'll change this to Vx. Minus Vx equals, sorry, back up. Minus Vx, minus V1, okay. All right, so that's Vx. So minus Vx minus V1 equals 0. And then I have that V1 is a minus 32. So Vx in this case is going to be 42 volts. Questions about that? Yes. Go ahead.
Is that a complete loop? How are you getting 0?
So my pathway is going through R2, through Vx, and then this volt, that's like through the multimeter, even though it's not drawn. So that's a physical connection through, it's just not drawn. So whenever you see that node, it means though that there's a connection from there to ground through a separate device, like a multimeter.
Whenever I see what node?
Any node like here, just at any of these nodes. So anywhere on a wire, anywhere in a circuit, if I write a voltage, that means from that point to ground is that voltage. As if I'd put like a battery there, but it's not going to conduct current through there, but it will have a voltage through there.
So could I do a CDL anywhere in the ground? Like I mechanically can do?
So, yeah, so I could say,
So you just skip the V2 when you do that?
so that's a separate, that would be a separate loop. So if I went through here, that gets me to V1, and then I have to go back to ground from that point. So that's where my V1 is. Does that make sense? Okay. Other questions? Yes.
So could you draw a loop with just R2 in it? Like, could you just end it at the yellow?
So the ending at the yellow would be that you go here and then you use V4, and that's in the reference to getting you back to ground.
And that counts as
Yep, so that loop would be, and then again, this is plus to minus. So you would have plus, I'll call it I2. Oops. I'm going to label it the same direction as that polarity. So this direction. So it's plus to minus are the same as that voltage. So plus I R2, and then it would be a minus. So this would be plus and then minus. V4 equals 0. Or you can say that V4 is I times R2.
It's not a CBL.
It's a voltage loop.
But when you do voltage, you're not adding up and moving to zero like a CBL. It's a different thing.
So a KVL,
Or KVL, sorry.
yeah, a KVL is that you take a loop from one point back to the point. So if you're going through different branches, that's getting you back there. So I go through R2 and then I go through what is unknown of the V4, which is a physical multimeter. So they're different branches getting you back to the same point. So here I could go, I could go through this loop, which would then get back there, or I could go to V1 and then go through V1 back to ground.
That's not a KVL, it's a voltage.
It's still a voltage loop. It would be considered a KVL loop. So either way, those would both be KVL loops. Okay, so let's look at V2. So V2, you don't know the current in R3, but you could find that. So if I labeled it this direction, I3, you could say that V2 is a plus here, and then for V2 of the label, it would be a minus. So plus I3 R3 minus V2, so that's one loop. Or I could go through V1, which puts me from ground to that point, and then through that element to V2, which then goes back to ground. So it goes from here to V1, through here, and then through V1 back to ground. So that loop, it would be from ground to this point is always a plus wherever the node is. So that would be a plus, plus, and then a minus. So plus V1 plus 48 minus V2 equals 0. So substituting in, this is minus 32 plus V8 minus V2 equals 0. So V2 will equal, is that 14? 16. Thank you. 16. I'm just showing you that if you knew I3, you could find this.
Oh, you're just calculating a voltage, IR.
Yeah.
Okay,
It's just IR.
okay, great.
Yep, it's just IR. Which is the voltage across that element. So they're kind of different pathways. All right, V3, I know the node here and I know the node voltage there. So I've shown you mathematically like how you can do KVL and look at it this way. It might not be as intuitive for some of you to see it that way. So another way to look at it is if I know one voltage on each side of an element, I can just use the polarities from plus to minus and say that difference, if I just measured it from there to there, is also that value. So plus side would be minus 32. So for V3, you could say it's minus 32 minus a 20. So this would be minus 52 volts. So that's another way of doing it. Or I can do the loop, full loops, and then it would be a plus V1, so plus here, a minus here, and then from here to here, it would be another minus. So plus V1 minus V3 minus, I'll call that I4. I4 times R4. But you know that that node that is also there is 20, so you know that 20 is equal to I4 R4. Does that make sense? Yes.
How did you figure out the, like the charge or like the plus or negative of the node at the top and the node at the bottom?
So V5, so anywhere in a circuit that you just have a dot, that's always going to be positive. It's always implied to be positive from that location in comparison to ground. So the plus there next to the V1 is because that's a node, and then to ground. And then also at V5, that's a plus because it's the node to ground. So that's the only, always a plus at that location. So even though V1's negative, I can still say it's plus and then substitute in the negative value. And I usually tend to say that's what I recommend for everybody, is just always put positive on the node and then relabel it once you've done your loop with the positive and negatives.
So when you did the loop for the purple one, and you did plus V1 plus 48 minus V2,
Uh-huh.
how do you know the minus V2?
So again, V2 node is a plus at that location in comparison to ground. So as I went through that loop, I went this direction. So I had the plus, and then the plus, and then going through V2 would be a negative. So use just whichever direction you're going in. So I could have done it going this direction, and it would have been a plus, minus, and then another plus. So the green one here, that pathway is a plus V2 minus 48 minus V1. And that will yield the same.
Is that the same?
Uh-huh, because you'll put V2 is equal to 48, and then this is a minus 32. Oh, wait. Did I go wrong? Plus V2 minus 48 minus, sorry, that is. So from here, it's a plus, and then it's a minus down there.
Okay.
Yeah, I mislabeled that one, sorry.
That makes sense.
Yeah. Okay. So yeah, it would be a minus on that one. So minus V1 equals 0, and then the minus in there becomes the plus, and then it's the same. Okay, other questions? Okay, so here we have just a string of batteries. So what is the bottom point? The arrow going down is another symbol for ground. So that would be what voltage? 0 volts. At V3, what is your voltage going to be there? 4 volts I would measure there. And that's in comparison to ground. What about at V2? Thank you. -4. Yes. -4 volts there. And then at V2, okay, so I add the 15 on there. So it's 15 added on to -4 for 11 volts. And then here, and then 11 plus 3 for 14. Is there current flowing in here?
Yes.
So it's just floating. These are batteries that are stacked up, but there's no connection, physical connection, except for through like a multimeter. But that multimeter is pretty much like not going to conduct. So we just say that there is 0 current here. So no current, but we can have voltages. Yes.
So you always move like from ground to the other point, like, cause that's what you're comparing it from?
Yep. So from here, V1 is going to be from that location in comparison to ground. So that's why I've been labeling that plus to minus. So anywhere you see that node, it's going to be that way. We could have it twisted though. So this could be the same thing. What's at V1 here?
14 volts.
Okay, same, right? -4 plus 11 and then 14 volts. So it's going to be the same even though it's twisted. So it doesn't matter which direction you're in. What about this one? What are you going to measure at V1?
16.
Okay, good. So -4, -19, and then plus 3 will be -16. Current? 0 amps. So voltage, you can have voltages without current, but you can't have current without having a closed loop. Okay. Okay, that's the same circuit. All right, questions? Yes?
So could you apply this to like finding V3 at the top on this top question? If I start at ground and just go to past V3, so it'd be what, 0 plus 20 minus V3 equals -32?
So it'd be a plus. So from wait,
So from
sorry.
V0,
V-
wrapping around the right side to V1.
Yeah, so from 0, so I have too many colors here, sorry. Okay, orange. So from here, going to here is 20 volts, and then you would add on whatever voltage this was to get to -32.
And you'll know it's negative. You're adding it, but it's a negative value, right?
For V3, yeah.
Because it equals -32.
Yeah, so you'd use a plus V3, and then that's substituting in a -52. Yep. So yeah, 20 minus 52 is going to give you that -32.
So you kind of treat the resistors here kind of like batteries in that other chart.
Again, like every element has a voltage and a current through it. So the resistance, other thing we know about resistance is we can also find the voltage if we know the current. And if we know the voltage, we can find the current through it. So that's helpful to know which one do we want to find. Okay. Is there any other questions? Okay. You guys seem to be kind of getting these, so I guess there's 2 of these. Delete one of them. Okay, so Now we're skipping ahead to current dividers. So determining a current IX in this bridge. So that's located here. So in this one, you need to identify where are your branches. Or sorry, this isn't a current divider. This is going to use KCL. So each of these are labeled. I'm going to give you another one. Find this direction. Also find this one. I'll label it IY. So go ahead and try and find IX and IY. And feel free to work with your neighbors. If you haven't met your neighbor, introduce yourselves. All right, so good job. You guys look like you came to consensus. One thing I saw was polarity. So making sure you have the right polarity. So in order to find IY, you have 3 coming in, and then IY and 1 amp go out, so that direction that's labeled has to be 2 amps. For IX, you have to put the positive or negative based on the labeling of what it is. So knowing now that IY is 2 coming in, I have all of these are going in. So I'm going to have plus IX, plus 2, plus 0.5. So this has to be a minus 2.5 based on the labeling. If I asked to find this current labeled this way, then I would have to look at either of these 2 sides, and it would be IZ going out, 3 going out, and IX going out. So they're all 3 of them going out. So then IZ would be a minus 3 minus IX, which is a minus 2.5 for a plus 0.5. If I did it from this side, I would have 1 amp coming in, 0.5 going out, and IZ going out. So, going in. Label that wrong. So IZ is going to go in this direction, and then it will go in this direction as it follows that wire around. So you need to make sure you, wherever it's labeled, you follow it around. So 1 amp going in, IZ going in, 0.5. So IZ is a negative 0.5. So the same. Oh wait, I did do my negative over there. Sorry. Negative 3 plus 2.5 is a negative 0.5. Is that why the person raising your hand? Did you catch that? Okay, that was my error. Okay, questions on this? Yes.
So with it being negative, does that mean that the actual flow is opposite that of the arrow?
Correct, but whatever it's labeled, just leave it there and put down the answer in the negative form of it. So if I had drawn it actually the other way, I would have found that result to be a plus.
Okay.
But if it's drawn, label it the polarity of whatever is drawn in there.
Keep it consistent.
Keep it consistent. If it's not drawn, then you'll get credit if you did put this like on an exam and you said I labeled it this way and this is the answer I found.
Right.
Okay. Yes. Sorry. If you can be quiet for just a second. Sorry, I couldn't hear you. What was that question?
For IZ, is it
Uh-huh.
negative 3 plus 2.5 or minus 2.5? Because we wrote 2.5 on this side. Negative. Oh, so I couldn't see that negative
Negative
side.
0.5.
Sorry, I couldn't see the negative side in front of the 2.5.
Yep, there's a negative in there too. All right. Have a good weekend. Make sure to do the quiz if you haven't yet today. I'll see you guys on Monday.